All right, welcome back to another calculus lecture. In today's lecture, what I want to talk about is a way of classifying the local extrema that we've seen in the past couple of lectures. So if we have a graph, we can look at where it has local maxima and local minima. But if I'm just looking at the derivative, maybe I don't have access to graphing software, I can't look at the graph. Well, can I use just the analytic statement of the first derivative, sort of expression for it, in order and decide through some process whether or not my critical points represent local maxima, local minima, or neither, something like this. And indeed we can do that, and the way that we'll do that is through the first and the second derivative tests. So both of these will actually give us the same information. Sometimes one is more computationally convenient to use than the other. So I want to show you both of them, but whenever I ask you to classify critical points as local extrema or local max or local mins, you are free to use either one of these. It will not matter. Okay, so let's go ahead and talk about the first derivative test. So the first derivative test, maybe before we write down the formal statement of it, let's take a look at the graph we had in the last lecture. So we have this graph, and I have, let's look at this leftmost point right here. There we go, there's my cursor. So if I look at this point, then, and maybe let's throw the first derivative up here, this yellow line. So I want to say that this first point right here is a local maximum. Well, notice what's true about the first derivative. My first derivative goes from positive, I'm above the x-axis, to negative. And this corresponds to the function being increasing and then starting to decrease. So maxima occur where the derivative is increasing and then switches to being decreasing. Or in the sort of language of derivatives, the first derivative is positive and is then negative. And likewise, a local minimum is the reverse of that. It is the first derivative is negative and then it switches to being positive. That is, I have my function decreasing and then it switches to being increasing. And this is precisely the content of the first derivative test. It just summarizes that information. So if we go back to our notes and write down the first derivative test, so let x equals a be a critical point of f of x. So we're at this point where the derivative is doing something interesting. So if, and we'll say it like this, so if f prime of x is positive for x less than a and f prime of x is negative for x greater than a, that is, my first derivative is positive, and then I move along and I switch to being negative. I realize I've just drawn an invisible sort of curve here, but hopefully the motion conveys what I'm trying to say here. So if I switch from being increasing to decreasing, then x equals a is a local maximum of f of x. And likewise, if f prime of x is negative for x less than a and f prime of x is positive for x greater than a, so I am decreasing and then I switch to increasing, then x equals a is a local max, or a local min, I'm sorry. It is a local minimum of f of x. Okay? And if we go back to our example that we looked at, this is precisely what's happening. If f prime of x is positive and then switches to being negative, I have a max. And if the reverse of that is true, if I'm negative and I switch to being positive, then I have a minimum. Okay? So let's maybe do an example of finding and classifying critical points So example, use the first derivative test to find and classify the local extrema of f of x equals, I don't know, x squared plus 1. We'll do something simple. So I want to find the critical points of this first. So step 1 is find the critical points. And to do that, we need to take a derivative. First thing we always do when finding critical points is take a derivative. So f prime of x is equal to 2x because x squared, the derivative, is 2x. And then 1 differentiates to 0. And then I set that equal to 0 in order to find where my critical points are. This is a polynomial, so there aren't any points where the derivative is undefined. So we can ignore any of those. So I just care about where the first derivative is equal to 0. And if we just solve this, I have that x equals 0 is a critical point. And it is the only critical point. And now I want to use the first derivative test. And in order to use the first derivative test, there are a number of sort of techniques that you can use. The way that I do this is with what's called a sign chart. Other people do this differently, but this is the way that I find it most natural, or perhaps it's just because it was the way that I was taught. But what we do is we draw a little table like this, and then I'm going to put the value of my critical point at this line, and I would do this for each critical point that I had. I'd draw another line. And then I'm just going to pick a test point on either side of this point. So maybe let's do -1 and +1, something where it's easy to evaluate the derivative there. Then f prime of -1 is -2. You just plug it in. F prime of 1 is 2. And really, I don't care too much about the exact values here. What I really care about is the sign of these numbers. And so this guy is negative, and this guy is positive. And then what I also like to do is draw a little sort of picture of what a negative slope looks like. So that just looks, the line looks something like this if I have a negative slope. And likewise, if I have a positive slope, then my line looks like this. It tends upwards, and if I have a negative slope, it tends downwards. And then I can just look at this sort of combined picture and say, oh, well, clearly x equals 0 is a minimum. I have this sort of shape right here. I'm at a minimum of my function. So, and if I look at the first derivative test and compare this analytically to what this says, then the derivative is negative, and then it switches to being positive. So I am at a minimum of my function. So by first derivative test, x equals 0 is a local minimum. Okay? Easy as that. That's all we have to do. So maybe let's do another example just to really get our hands dirty with the first derivative test and get comfortable with it. Okay, so example. Same as before, but f of x is now going to be equal to 3x to the 4th minus 4x cubed plus 7. Okay, so first thing we do, let's differentiate. So f prime of x is equal to 12x cubed minus, so 4 times 3 is 12x, and then 3 times 4 is also 12x, or is 3 times 4 is 12, not 12x. So minus 12x squared. So each time I've applied the power rule, and I just happen to get the same coefficient in front. And then the derivative of 0 is 7. So let's go ahead and set this equal to 0. Well, I'd like to factor this, and I noticed that I can actually factor out a 12x from 12x squared from each of these two terms. So f prime of x is equal to 12x squared. I get x left over from my first term and a 1 left over from my second term. So I'm just going to have an x minus 1 right here. And when I set that equal to 0, I find that x equals 0 and 1 are only critical points. There aren't any critical points where the derivative is undefined. I have a polynomial, so the only critical points are where it's equal to 0. And those 2 points are x equals 0 and x equals 1. So let's go ahead and make our sign chart here. So we'll put in 0 and 1. And we pick convenient values on either side. So let's do -1, 2, and a half, maybe. You know, nice simple values. So f prime of -1, I go up here and I plug in -1. Well, 12x squared is going to be positive, right? If I square a negative number, I'm going to get a positive number. And then if I plug in -1 right here, I'm going to get -1 minus 1. So I'm going to get a negative number. So the really important thing is that this number ends up being negative. And you can do this on a calculator if you don't like to do that kind of reasoning. But I find it easier to just sort of look at each individual factor and think about its sign. Okay. If I put in a half, again, this first factor is always positive, so it's only the second factor that is going to govern anything. So f prime of 1/2, well, 1/2 minus 1 is -1/2, so this is negative. And if I put in 2, again, we have positive here and positive for the second term, so f prime of 2 is positive. And so if I draw my little lines, then in fact what I have is that that 0 is not a local max or a local min. The derivative is not changing sign at that point. It's momentarily 0, but then it just goes back to being negative. It actually switches sign at x equals 1. So by first derivative test, x equals 1 is a local. And let's think about this. I'm decreasing and then I'm increasing, so I'm going to have a local minimum here. And x equals 0 is neither a max or min, because the sign of the derivative doesn't actually change. It's decreasing, and then it's 0, and then it continues to decrease. So a graph of this. Okay, so it's been a long day and I just made a really silly mistake. So the graph of this is going to look something that's roughly like, I come over here, I have my 0, here's 1, 0 and 1. The graph is going to decrease. It's going to sort of flatten out at 0, but then continue to decrease, and then hit a local minimum at x equals 1. Something like this. I've really stretched out the graph here horizontally, but this is roughly what it looks like. It sort of comes over here, the derivative flattens out, but then continues to decrease over to 1 where it has a local minimum. Okay, so this is roughly what this looks like, and this shows you that the first derivative test doesn't always give you that every critical point is a local extrema. Sometimes you have this business happening where you don't have local extrema being or critical points being local extrema. Okay, so let's go ahead and move on to the second derivative test. So this is just another method of computing these things. And if we go back to our picture over here, then, and let's go ahead and pop the second derivative on here. Then look what happens at this local maximum and this local minimum. So what do you notice about the derivative or the second derivative at this point? The second derivative is negative. It is below the x-axis at this point, and the graph is concave down there, which makes sense, right? The graph should be opening downwards if I have a local maximum. Likewise, if I have a local minimum, the graph should be opening upwards, and my second derivative should be positive. So let's go ahead and just summarize that in the second derivative test. And that is precisely just the content of the second derivative test. the second derivative test. So let x equals a be a critical point of f of x. I don't know if you all just heard my roommate. That was a very strange noise. So if f double prime of a is positive, so if I'm opening upwards, then x equals a is a local minimum. And if f double prime of a is negative, then x equals a is a local maximum. So it's a little bit reversed of what you might immediately think when you read this. So if the second derivative is positive, I should have up, so max. No, that's not actually what happens. If you're opening upwards, you have a minimum, and if you're opening downwards, then you have a maximum. Okay, and if you think about this graphically, it makes perfect sense, but I've seen students sort of get tripped up on this, so just be careful when using the second derivative test to not make that mistake. The nice convenient thing about the second derivative test is I don't have to sort of pick these test points like I do in the first derivative test. I can actually just evaluate the second derivative at this point and figure out, you know, am I at a local max or a local min? Also, I should say, if f double prime of a is equal to 0, the test is inconclusive. So it is possible, like I showed in the last lecture, to have the second derivative equal to 0, but I'm not actually at a critical point or something. You know, I can be at an inflection point, and that inflection point might also be a 0 of the first derivative, and when I evaluate the second derivative there, I might get 0, but that doesn't tell me anything about the shape of the graph at that point. Okay, so if you get 0 from evaluating the second derivative, then you have to do essentially the first derivative test to figure out are you at a local min or a local max. So let's go ahead and do an example, and we'll use the same function as before. So use second derivative test to classify the extrema of, I should say local extrema, oh well, 3x to the fourth minus 4x to the third plus 7. So I want to use the second derivative test, and for that I need my critical points. So as before, 0 and 1 are the only critical points. Okay, we just saw that in the last example. So now we need to actually compute the second derivative. So the first derivative we saw was 12x cubed minus 12x squared. Well, the second derivative is just going to be, well, 36x squared. So 3 times 12 is 36, and then I drop the power by 1, and then I have 24x. So I drop the power by 1 here. 2 times 12 is 24. Now I just need to evaluate my derivative, my second derivative, at each of these 2 points. So f double prime of 0 and f double prime of 1. Well, f double prime of 0 is easy. It's just plug in 0 for each of these. It's going to be 36 times 0 squared plus minus 24 times 0, which is equal to 0. And likewise here, the second derivative evaluated at 1 is just going to be 36 times 1 squared minus 24 times 1, which is just 36 minus 24, which is 12, and that's positive. So by second derivative test, x equals 1 is my second derivative is positive, and so I have a minimum. It's exactly what we found before. And x equals 0 cannot be classified, because the second derivative is 0, so we're not quite sure what is happening there, and we need to look at the first derivative test in order to figure that out. Okay, so these are the first and second derivative tests. These are ways that you can classify the critical points of a function as local extrema, local mins or local maxes, without having to look at the graph itself. You can just do this sort of analytic process and then determine whether or not you're at a max or a min. Okay, so in the next lecture, we'll look more at how to study the shape of a graph, and then eventually we'll actually try and sketch some graphs from using just the function and its derivatives. All right, so see you all in the next lecture.